Assignment 4.4. So without using a calculator, find the local extrema, points of inflection, sketch the graph, show organized steps, justify it. It is not necessary to find the intercepts. There are no domain restrictions or asymptotes. However, an end behavior analysis might be helpful to know where the ends are going. So here's a polynomial. I want us to analyze and graph it. So I'll go back and forth between this and my document cam. So, okay. So if I want to find the extreme points, the relative turning points, we're going to take the derivative, make it equal to 0, and we're going to solve it. So I'm going to factor out 3x, solve it, and at 0 and 2, I have critical numbers. I'm going to do a first derivative number line. I'm going to create my intervals to know where is the graph increasing and decreasing. So into the derivative, if I plug in a negative answer, negative number, that's a negative times a negative, which is positive. If I plug in positive 1 for the next interval, that's a positive times a negative. And if I plug in a number bigger than 2, you'll get a positive answer. So the graph increases, decreases, increases. So what did I learn? So at 0 is a local maximum. At 2 is a local minimum. So let's find those right now. So the x coordinate of the maximum is 0. Go back to the function itself, plug in 0. So 0, 5 is a maximum. There's a relative minimum at 2. If I plug 2 into here, I'll do it in my head, that's 8. 2 is what, 12. So 8 take away 12, negative 4 plus 5. So at 2, 1 is a relative minimum. So I want to find the extreme points. What do? Take the derivative equal to 0. Those values are critical numbers. They go on a first derivative number line. In your intervals, test to see if the answer is positive or negative. And it tells me where it increases and decreases. Where it changes from increasing to decreasing creates a maximum. Where it changes from decreasing to increasing creates a minimum. Next, we're going to do the second derivative. So that would be 6x subtract 6 equal to 0. If I solve that, you get the answer 1. So there's only one critical number to check out. Into the second derivative, if you plug in a number less than 1, the answer is negative. If you plug in a number bigger than 1, the answer is positive. That right there, because of the sign change, creates a point of inflection. So the concavity goes concave down to concave up. Plug positive 1 into here. That's 1 take away 3, negative 2 plus 5. I think it's 1, 3. So we have a point of inflection at 1, 3. What else might be helpful? The end behavior might be helpful. So when I do the graph, we'll talk about end behavior. Let's just do what we have so far. And then think about increasing, decreasing concavity, and so on. So 0, 5, 2, 1, 1, 3. So don't worry about the intercepts. So we already know y-intercept. Don't worry about that. Just the curve of the graph is what we're focused in on. So the end behavior of the power term is positive with an odd exponent. So the right end goes up and the left end goes down as I'm drawing it. So this graph increases with a frown. So I'm going to increase with a frown, and it frowns all the way to 1. But at 0, instead of increasing, it decreases. So I can see this part of the graph to begin with. The left end goes down, so it increases, it turns, but it's concave down the whole way. After 1, it's going to be concave up, and at 2, it's going to turn. So now it's concave up, it's going to turn, and notice the right end goes up and the left end goes down, and you've graphed it. And this x-intercept, I'd have to make it equal to 0. It's not obviously factorable. It's probably irrational. You could look off a graphing utility to find it and solve it. I think that's everything. Number 2. So pretty powerful stuff. Calculus, to be able to graph without a calculator. Let's go back here. Number 2. So 1 subtract x cubed. We're going to go through the same steps. Here's the document cam. So step 1, I'm going to take the derivative. That's -1 minus 3x squared. I'm going to take it equal to 0. So in this situation, I can add 1, divide, and then what happens? So when I add 1 and divide, this will give me an answer that is complex or imaginary. For calculus, we're not dealing with that. So on a graph, what does that tell me about critical numbers? So for number 2, are there any critical numbers? So the answer is no. So if I do a number line for the first derivative, there are no critical numbers to put on there. This is monotonic. It's either all increasing or all decreasing. So how would I know which way it's going? Plug in any number in here. So whether it's a negative number or a positive number, and the answer will always be negative. This is always decreasing. There are no turning points, no critical numbers. Second derivative, that would be just -6x. So when I divide, I get 0, so I do get a critical number for the concavity. So for the second derivative, if I put in a negative number, a negative times a negative is positive. Put in a positive number, you get a negative answer. So you can see the concavity and that there's a point of inflection at 1 or at 0. So then plug 0 back in and you get the answer 1. So the point of inflection at 0, 1. Now we're ready to graph. Just the end behavior. So the only point I really have there is 0, 1, so I'll put that there. What's happening to the right and left? So we'll start with the right of it. To the right of 0 is concave down, and it's decreasing. Notice here the power term is -x cubed. So the right end goes down, and the left end goes up. And the concavity changes at 0, 1. So it's concave up, concave down, but the whole thing is decreasing. That's it. And this x-intercept, again, it's not obviously factorable. It's probably irrational. You could use a graphing calculator to figure out exactly. But we're just thinking of the behavior and curve of the graph. And using calculus tools. All right, one more like this. Number 3, y equals x to the 4th, subtract 4x cubed plus 16. So step 1, we're going to take the derivative. We'll make the derivative equal to 0. We're going to solve this by factoring. So we're going to factor out a 4x squared. Solve it, and you get the answer 0. So 4x squared gives you the answer 0. X subtract 3, positive 3. Do a number line for the first derivative. Plug in to the second derivative. The factored form might be easier. A negative number. So a negative number will be positive times a negative. Plug in positive 1, a positive times a negative, and then any number bigger than 3 will give you a positive answer. So it decreases, and then it only here. So there's only one turning point. So at 3 is a minimum. It decreases and then increases. This, there is no turning point because the signs didn't change. So we only have a relative minimum, and it's when x is 3. To find the y coordinate, plug it in. I'll do it for you. But plug it into the equation. So it's 3 to the 4th and 3 cubed times -4 plus 16. So there's a minimum if you did that at -11. So if you plug 3 into here and did the work, you get -11. The second derivative is 12x squared minus 24x. Again, make it equal to 0 and factor. So the two answers you get here are 0 and 2. So this is for the second derivative. So into here, if you plug in any negative number, you get a negative times a negative. If you plug in positive 1 in the interval, you get 12, or you get positive times the negative. And any number bigger than 2 is positive. So the concavity changes. So both of these create a point of inflection. So at 0 and at 2. So if you plug 0 in, you get 16. If you plug 2 in, you get 0. Well, that's nice. That's a x-intercept for free. So if you plug in 2, you get the answer 0. Well, we're ready to go. The only thing we have to think about at the end is maybe end behavior. So the end behavior here, positive with an even exponent, both ends go up. So we have 2, 0, we have 0, 16. We'll just put it up there somewhere. 3 and negative 11. Just sketching it. And now connect the point. So to the right is concave up with the turning point. So this is concave up with the turning point. So you can see there's going to be another x-intercept here, which we don't know, and we did need to know. So curve up, notice with the turning point, that's a minimum. Now we're going to, so one turning point right here at 3. Make sure I'm thinking straight here. Then from 0 to 2, or from 2 to 0, it is decreasing, but with so it's decreasing, but concave down. And then it does not turn to come back down, so both ends go up. So concave down, and then to the left of 0, it's concave up, but still decreasing. So notice it decreases all the way to 3. See how it decreases all the way to 3. Concavity, concave up, concave down, concave up. So it changes how many times. And then at 3, there's only one turning point, and it's part of the concave up. A little challenging, right? To follow the concavity, to follow the curve. It just takes some practice. Number 4. Find intercepts and relative extrema and graph these functions without using a calculator. So we want to find the intercepts and the extremes of the graph. The concavity, these are concave up, right? And then the absolute value is the same one. But anyways, concavity, we'll figure. We know it's concave up because it's positive x squared. So to find the extremes, take the derivative. That's 2x minus 2 equal to 0. If you solve this, there's an extreme point at positive 1. Now I already know it's concave up, but if you tested it into here, a negative and a positive at 1 creates a minimum vertex. But you knew that already because it's concave up. So we have a minimum, or it's actually an absolute one because it's a parabola. So an absolute minimum at positive 1, that's the vertex. Plug it in and you get negative 9. So at 1, negative 9, you have a minimum. If you want to find the intercepts, plug in 0 and factor it. So we have x-intercept at 4, 0 and at negative 2, 0. If I plug 0 in, I have a y-intercept at negative 8. And that's it. So 1, negative 9, 0, negative 8. You can reflect it over the axis of symmetry if you want. We have 4. And negative 2. Draw your parabola. and you found the extreme points, the turning point, which is another name for a vertex. You found the intercepts, and then if you took the derivative of this, it would be positive 2, right? The second derivative. So no matter what number you plug in, the answer is always positive, so you can see the concave up throughout. Now, what makes number 5 different? It's just the absolute value. So if I want to graph the absolute value and I just know the regular graph without the bars, it just reflects whatever is below, it reflects up. So the lowest point was 1 and negative 9. That becomes 1 and positive 9. So that reflects up. And then these negative points reflect up. So at, what is it, 0 and negative 8 becomes 0 and positive. But these intercepts, which are at negative 2 and 4, they stay, because the answer 0 stays on the axes. But how would it look? So I just want you to make sure that you understand just that parabola is reflected up. So kind of looks like a W. But this part that was below got reflected up. That's what it looks like. For the extreme points, we now have a relative maximum. And that relative max is at 1 and positive 9. That's a turning point. And we have, because of that, we also have turning points down here. Those are relative minimums. So that means now the intercepts are turning points. So at negative 2, 0, and 4, 0, we have relative minimums because of that reflection. So now we've created 3 turning points. Number 6. Find the extreme points, points of inflection, and behavior in graph. So all that good stuff. But for a rational, just writing down the second derivative. All right. I think it looks worse than it is. Well, maybe it is bad. So we have a rational function. We want to find the extreme points. That's the first derivative. I have to use the quotient rule. That's the bottom times the derivative of the top minus the top times the derivative of the bottom, and then the bottom squared. Let me just simplify the numerator just a little bit. That's 4x cubed. That's minus 4x. So 4x cubed minus 4x cubed. So if I multiplied out 4x cubed minus 4x cubed, they eliminate. So all I'm left with on top is 12x. If I made that equal to 0, you only need the numerator. So what makes the numerator 0? So 12x equal to 0. The only critical number is at 0. That makes the whole thing 0. So if I do a number line, only 0 for the first derivative. Now, by the way, if I plug in 0 into here, the second derivative, if it's positive or negative, it tells me the concavity right away. So I might want to do that. So to make my life a little easier, plug in 0 here. If you plug in, this is the second derivative test. If you plug in 0, you get a negative times a negative, positive. The bottom is positive, so it's concave up. So if it's concave up, it must be in this direction. And you could do it from here too. So 0, if I plug into the function, gives me the answer 0. So at 0, 0 is a minimum. If I look at the second derivative, it's already been done for me. X squared subtract 1 is a difference of squares, so I just have to make sure it's completely factored. If I look at the numerator and make it equal to 0, I have 2 critical numbers, positive and negative 1 for concavity. So I'm going to do a second derivative number line using negative 1 and positive 1. If I plug in a number smaller than negative 1, you would have a negative times a negative times a negative. That would give you a negative answer. If I plug in 0, you'd have a negative times a positive times a negative. And if I plug in a number bigger than 1, it'd be a negative times a positive times a positive. So that's the concavity. So at -1, we have a point of inflection. So if I plug -1 back into the function, I get 1/2. So if you plug -1 back into here, you get 2/4. If I plug +1 into here, I get the same answer, 1/2. So both negative and +1 give me 1/2. Those are points of inflection. If I look at the power here, 2x squared over x squared, I can tell that at y equals 2 is a horizontal asymptote. That's the end behavior. So again, 2x squared over x squared, they have the same power. Divided out, you're left with 2. That gives you the end behavior. Let me just do a quick sketch of this. So 0, 0, 1.5, -1.5, just like that. See, they should be around the same height. And then at, what did I say, 2. So the end behavior is going to 2. So when I think here, in terms of concavity, so in the middle between -1 and +1, it's concave up with that turning point. So I'm just going to go concave up between -1 and 1, and then it's concave down, and then it's concave down. So notice the concave down and concave down. So it decreases and then increases, and you have your graph. Do you know that if you needed to, you could go back to the beginning of the question and go slower and go over it a second time, a third time, 100 times. Don't do it 100 times. But if you had to, if it was a particularly complicated question, you could go back and go through it again to see if you can do the calculus and some pre-calculus to be able to organize and graph this without a calculator. You could also type this into Desmos and see if I'm doing okay without a calculator. Number 7. In number 7, it says f at x equals x squared plus 1 over 2x. For this one, it says find the domain. So I'm just going to talk about it out loud. Look at the denominator. It's all real numbers but 0. So 0 is the only one that would not work for the domain because 0 would make it undefined. There's an asymptote at 0. So if we want to know about a vertical asymptote, it's at 0. Relative extreme points, I need to find the derivatives. Let's go over here in end behavior. So I already know that the only restriction is 0, and that creates a vertical asymptote. Derivative is the quotient rule. That's the bottom times the derivative of the top minus the top times the derivative of the bottom, and then the bottom squared. So if I simplify that, I get 4x squared minus 2x squared minus 2. The bottom is 4x squared. If I keep going, 4 take away 2 is 2x squared minus 2. It might be helpful to do this, so I'm going to simplify it one more step. Divide a 2 out. Like if you factor out 2 and divide it out, you get x squared minus 1 all over 2x squared. The top is a difference of squares so that you can see the critical numbers easier. So this numerator, if you factor out a 2, right, we have x squared subtract 1. So I'm just taking a 2 into 4 2 times. And then what you're left with is a difference of squares. So when you solve this, so if you made it equal to 0, just look at the numerator. So the two critical numbers are positive and negative 1. That's what makes the numerator 0. Do a number line. Into this, if you plug in a negative number, it would be a negative times a negative. The bottom will always be positive. Plug in 0, and it would be a negative. Plug in any number bigger than 1, and then you can tell the turning points. So at -1 we have a maximum. So if I plug -1 back into here, I get 2 over -2. So at -1 is a maximum. And then the other one gives me a minimum, a relative minimum in its area. So +1 gives me 2 over 2. So it's 1, 1. So we have -1, -1, 1, 1. Those are my minimums. If I want to find the second derivative, so if I took this and found the second derivative, that's the bottom times the derivative of the top minus the top times the derivative of the bottom, and then the bottom squared. Just focus on the top. You would have 4x cubed. Here you would have minus 4x cubed when you multiply it out, and then you'd have plus 4x. And then when I simplify that, the 4x2's, and you have 4x over that, the 4x's would divide out. And you'd be left with this as your second derivative. There is nothing here. If you made that equal to 0, there's nothing to solve. So there's no point of inflection. So there is a place where it's undefined, though. So it's undefined when x is 0. So 0 makes it undefined, which makes it a critical number, but it's not a point. So if you test negative or test positive, you put a negative number in, it'll be negative, and a positive number will be positive. So 0 is where there's an asymptote. So it's not a point of inflection, but it does tell me about where it's concave up and concave down. Then I'm going to put this together. So we have -1, -1. I have +1, +1. I have an asymptote at 0. And I have another asymptote too. So if I look at the beginning part of the question, x squared over 2x squared. Nope, sorry. Way back at the beginning. X squared over 2x. That's one I should be looking at. So if I take power term over power term for the M behavior, notice the top is more powerful. So if you divide out the power terms, you have basically 1/2 x. So x squared and x, if I just take power term, x squared over 2x, it leaves me with 1/2 x. So what that really means for my M behavior is that it's like a slanted line. The top end goes up and the bottom part goes down. So I know my behavior here. There are no x-intercepts. So if I take x squared plus 1 equal to 0, it's imaginary. So it doesn't touch or cross. So at the vertical asymptote, it goes to infinity. So there it goes to infinity. It turns. Remember, it's concave up. It turns and goes up. Think of this like a line that's like at y equals 1/2 x. Here, the same thing. And it turns. And you can see that part in terms of that the right end goes up, the left end goes down. This is concave down with a local maximum. This is concave up with a local minimum. Tricky, right? I think you love graphing, love putting the pieces together. Again, we can go back to the beginning and go through it all. That took up a good page right there. On to the next page then. What number am I at? 8. I'm only at 8. It feels like I've done 100 questions. 8. You can always press pause and come back to the assignment. Oh, wait. Number 8. Scroll down a bit here. Or up. Make sure I know what I'm doing. Find the domain. Reduce the function. Find if there's a hole. Intercepts. Extreme points. Oh, man, this is all the good stuff. And it's a fun equation to just go one step at a time and put the pieces together. So we're going to start with a great attitude, and we're going to figure this out. Okay, so if I want to graph it, let's just start first with the intercepts. So first of all, we're going to reduce it down and the domain restriction. So look at the denominator. X can't equal 0. That's a good start. Does anything divide out? Yep, the x squared and the x divide out. That leaves me just x. 4 subtract x, and it'd be a 1 underneath, but I don't need that. So the x goes into x squared. That gives me just x. And the square root of 4 minus x. And the denominator is 1, and I don't need to write that down. So this is my new function after you reduce it down. So because something was removed from the bottom, it creates a hole. So what was removed was x. Make it equal to 0. That's the hole at 0. If I put 0 in here, 0 times 4 is 0. So there's a hole at 0, 0. Next, we're going to take the derivative. Well, let's find the x-intercepts. If I make it equal to 0 and solve for x, take each factor. So like 1 is 0, but that's not going to be an intercept because that whole 0 is a whole. And then the square root of 4 minus x, make that equal to 0. So if you square both sides, 0 squared is 0. If you add x to the other side, you can see that at 4, 0 is another intercept. Now it happens to me that's also the end of the graph. Oh, x can't equal 0. Sorry, the other part of it is that x has to be less than 4. And so why must x be less than 4? Because if you plug in a number bigger than 4, you get a negative answer under the square root sign. So not only can x not equal 0, x must also be less than or equal to, could it be equal to 4, but it can't be bigger than 4. Oh, the derivative. So if I take the derivative, I need to write this so it's calculus friendly. That's the first times the derivative of the second. It's going to be the chain rule. Plus the second times the derivative of the first. And make that equal to 0. So we're going to factor out a 4 minus x. Oh no, what are we going to do here? Let's see what we're going to do. Make sure I don't lead you down something you shouldn't do. All right, let's write this as one fraction. So when you take the derivative, let's write this as one fraction. So we have x, and in the bottom we have 2 and the square root of 4 minus x. And I have the square root of 4 minus x here. To solve this, a little tricky, I need the denominators to be the same. So for the denominators to be the same, I'm going to multiply by 2 times the square root of 4 minus x. Now, when you multiply 2 roots and they're the same, they just undo each other. So you end up just with 4 minus x, no square root. That's one of those square root properties. And now you have one fraction. So now we're almost there. 2 times 4, that's 8. And then we have x and negative 2x. So it's 8 minus x. That's what I get. So 8 minus 3x. I get 8 minus x. I get 8 minus 3x. Just let me think. Why would it be 8 minus 3x? So why would this be negative in front? That's what I'm looking at. So let's make sure I took, oh, because you know why? I know why. So when I took the derivative, there was a negative 1 there that I didn't take into account. So it's really negative 1 times x. So this is negative x. Now I see it. So it's 8 minus 3x. So 2 times 4. 2 times negative x is negative 2x. Subtract x. And now, because it's a rational, all I need is the numerator equal to 0. So if I add 3x and divide 8/3, which is almost 3. So all that work to get to like a number line for the first derivative, just 8/3. So for only 8/3, oh, and 0, because at 0 it's undefined. Actually, I don't even need 0. So, because there's a hole at 0, it's undefined in there, but ultimately, if you plug in a number that's smaller than 8/3, look here. So the bottom will always be positive. If you plug in like 0, you would get a positive answer. So this whole thing here would be increasing. Plug in a number bigger than 8/3. You can't plug in a number bigger than 4. So if you plug in like 3 into here, you get a negative answer. So it's concave, it is increasing and then decreasing. So at 8/3 is a max. To find the y coordinate that goes with that, you go back to the beginning. I'm going to do the work for you. So you would plug it back into here, 8/3. To find the y coordinate. So if I do that, and I won't blame you using a calculator or anything like that, you would get around 3, like 3.79 if you used your calculator. So around 3 is what answer you would get. We still need to do the second derivative. So let's do that. So right now we have a relative max. Let's do the second derivative. So the first derivative is 8 minus 3x over 2. Doing this. So the second derivative, this is some work. It's the bottom times the derivative of the top minus the top times the derivative of the bottom. So if I took this to the 1/2, 1/2 times 2 would just be 1. So it would just be 4 minus x, and then subtract 1 from the exponent, and you would have a negative 1 as a hook-on factor, because the derivative of negative x is negative 1. And then you would square this. And then you would make it equal to 0. And you would solve it. So, if you dare simplify this, and here's the truth. If you just took this equal to 0 with your calculator, you would get the answer 16/3. And it can't equal 16/3, because 16/3 is not in the domain. So if you took this in your calculator equal to 0, for now you can just trust me, that you would get 16/3. But the problem with 16/3 is that it's not in the domain, because you can't have any number bigger than 4. And 3 goes into 16 more than 4 times. That means there's no point of inflection. That means it is monotonic in terms of concavity. So if you plug in, the only concavity when you plug in and simplify this is that every time you plug in a number, it will give you a negative answer. So it's concave down throughout. This is a tough one, tough example, just because there's so many parts that are just can drag you down. So let's just get through this question. So how would I graph this? At 0, 0, there's a hole. At 4, there's an intercept, and that's it. The graph ends there. We said there's a max at 8/3, which is almost 3 and almost 3. That's a turning point. So this point I estimated here, and then so it ends here and it continues there. So it's decreasing, concave down. Sorry, increasing, and then concave down throughout. Crazy. We're just moving on. Number 9. Is number 9 any better? I hope so. I think so, yeah. Number 9's better. Number 8 was a tough one. It's okay. Sometimes you need a tough one. Sometimes you don't. Number 9. Without a calculator, domain intercepts extrema. So we have f at x equals the square root of 9 subtract x squared. And domain, let me just write it down, x-intercepts and extreme. There are no points of inflection. And graph. All right, let's do this. So first of all, the domain, see what's underneath there must be positive. So 9 minus x squared must be greater than or equal to 0. So you could subtract 9, and when you divide, the sign flips. And when you take the square root, this is what you get. Now, for when it's less than or equal to, it creates this situation where the domain is between -3 and +3. And then you test it out. Make sure it makes sense. If I plug in a number bigger than 3, you're going to get a negative answer. If you plug in a number smaller than -3, you're going to get a negative answer. So it's only valid from -3 to +3. So I set up the inequality and then solved it. I'm just going to do interval notation. The ends count. So you can plug in 3 and get 0, that's okay. X-intercepts, if you made that equal to 0, oh, I did that. What answers do you get? So you get positive and -3. Those are your x-intercepts. And I already did the work here just with inequality, but it would be the same steps. Just put an equal sign in, and you get positive or -3. All right, derivative. So first, that is 9 minus x squared to the half. So that's 1/2, 9 minus x squared to the -1/2, and then the hook on, which is -2x. I'm going to simplify it. 1/2 and -2 is -1x. And because I'm doing algebra, I'm going to write this as a fraction. So the negative exponent, I'm not going to do that. So -x, and this is actually the square root. Just like that. Make it equal to 0. Notice the numerator. So the only thing that makes this 0 is when the numerator is 0. And if you take -x equal to 0 and solve it, at 0, we have a solution. So that's the only one, and actually no arrows, just -3 to +3. 0 is the only one. If I plug in a negative number into here, you get a positive answer. If I plug in a positive number, I get a negative answer. So at 0 creates a relative max. So over here, 0 creates a relative max. When I plug in 0, I get the square root of 9, and that's a maximum. In fact, it's going to be an absolute max when you look off the graph, the highest point. And he said there's no point of inflection to worry about. If I want to know concavity, to take the second derivative, I think when you see the points, you'll see it's concave down. So we have +3, we have -3, we have 0, 3. What does that remind you of? And the answer is, when you connect it, it's a semicircle. So you can see it is concave down. If you had a full one, it would be right. You could draw a full circle. But if you drew a full circle, it wouldn't be a function anymore. So this is an equation of a semicircle, and we have that there. Whew. You know what? If we do it together, we can get through this. All right, next question. What? We're done the tough questions. Now the easier questions. So the question is, true or false, if the derivative is greater than 0, which means increasing, then the limit as x approaches infinity for f at x equals infinity. So what's it asking is, if the derivative is greater than 0, meaning you have a situation that is only increasing, that means it must go to infinity, right? It goes up forever. Is that true or false? And the answer is it's false, that you could have a horizontal asymptote that would be increasing. So notice that it is increasing, but it is not going to infinity. It's going to whatever the asymptote is. Number 11. It says find the discontinuities. So for number 11, just the denominator equal to 0 and solve it. This one isn't bad because you can factor it. So I need you to factor it and then take each factor and then solve it. And which ones are removable? Well, that one's a little bit more challenging. So if they're removable or not, then I have to put the factors back in. Let me show you the work I've done. So if you take the denominator and factor it, so if you take the denominator, x squared subtract 3x plus 2, here's the factors, negative 2 and negative 1. So this is removable. So it's not continuous at x equals 2, but it's removable. That means the limit exists there. There's also one at x equals 1. That one is non-removable because it's just stayed there. So at positive 2, it's removable because it got removed, but it's still a discontinuity. It makes a hole. The limit exists there. And x minus 1 remains, so it's non-removable. So there's two discontinuities. Number 12. In number 12, you have a piecewise. So where are there any discontinuities? Each piece is a polynomial. So each one by itself is continuous. So I just need to check where it breaks into two pieces. So I need to know the limit as x approaches 0 from the right. I'll show you what I'm writing down in a second. The limit as x approaches 0 from the left. This is what I'm writing down. So for continuity, I need to look at the limit from the right, the limit from the left, and what it is when you actually plug in 0. So from the right, when you plug in 0, from the left, when you plug in 0, already it's not continuous. And when I plug in 0, I'm not sure if that was the top piece or the bottom piece. Top piece. So if I plug it into the top piece, these have to agree, be all the same answers. They're not, so it is not continuous. So there's a discontinuity, a jump. At x equals 0. Because it's a jump, because the limit doesn't exist, it is non-removable. (13) That is a greatest integer function. Kind of weird notation. I use like the double bars for greatest integer. So for the greatest integer less than or equal to So all multiples of 3. And it's non-removable because the limit doesn't exist at a jump. So if you plug in any multiple of 3, you get an integer, and at every integer there's a jump. So all multiples of 3, and it's non-removable because the limit does not exist at a jump. 14. Find these limits without a calculator. So the limit as x approaches 2. So step 1 is if you substitute it in. And if I do that, it is indeterminate. It's 0 over 0. So I'm going to factor. So if I factor the denominator, it's a difference of squares. Then you can remove, and then you can solve. So this is what it looks like. So if I plug in 2, I get 0 over 0, which is indeterminate. I factor. I remove x minus 2. When I plug 2 back in, I get a quarter, and I have my answer. That's what the limit is equal to. Step 1 is it's a substitution problem. Then we do algebra. The limit as x approaches 2, x plus 2 over x squared subtract 4. For this one, when I look at it, and I do 2, it is not indeterminate. If you plug in 2, you get 4 over 0. Do not write down 4 over 0. That's bad math. But you can say it doesn't exist because it's not indeterminate. And even if you reduced it down, when you plug in 2, it'd still end up with a 0 in the denominator. So you'd only go further if it was indeterminate. 4 over 0 is not indeterminate. It's undefined. It's over. It doesn't exist. Here, when you plugged in 2, you got 0 over 0. That's the difference. 16. The limit as x approaches infinity of x plus 2 over x squared minus 4. This is a fancy way of saying the right end behavior. Power over power. Because the bottom is more powerful, this is approaching 0. If they were equally powerful, you would divide the power terms. And if the top was more powerful, we would divide and see the end behavior. But whenever the bottom is more powerful, the end behavior is 0. It's done. 17. Find an equation of the tangent line. And you could use your calculator. So, find an equation of the tangent line. The graph is y equals 4 to the x minus 2. X equals 5. Let's go from there. So I'm going to use my calculator. So first of all, if I want to find the y value, plug in 5. 5 take away 2 is 3. So 4 cubed, that's 64. Then use your calculator, and we want to find the derivative at 5 for the slope. So I'm just going to use the calculator for that, if that's okay. So I'm going to press menu. I'm going to go calculus and derivative at a point, and then the x is the value is at, what did I say, 5? And then I would just type in 4 to the exponent x subtract 2. Control enter. 88.722. You don't have to round. So 88.722. And then put it together. Y equals the slope, 88.722, x minus 5, plus 64. Done. Number 18. Number 18 says find the points at which the graph has horizontal tangents. So we have x squared plus 4y plus 2y squared equals 6. And then determine whether these points are local, minimum, or a maximum. Show work using the second derivative. and 19 is connected to it with vertical tangent lines. Okay. Here we go. So first of all, in order, you see the word tangent, it means derivative, so I need to take the derivative. So let's do that first. Because the x's and y's are mixed together, this is an implicit situation. So 2x, whenever I take the derivative with y in it, it needs the hook y prime. So follow along. 4 needs a y prime. 4y, but it needs a y prime, and the derivative of 6 is 0. Then I'm going to factor out a y prime out of this 4 and 4y. I'm going to subtract 2x, and then I'm going to divide to get y prime by itself. So the first question was, where are there horizontal tangents? At what point? So horizontal tangent means a horizontal line, means the slope is 0. So if I made this equal to 0, when the x is equal to 0, everything is 0. But then I'd have to come back here and plug in 0 for x and solve it. So if I plug in 0 for x, I'm left with 4y. 2y squared equals 6. So I still have some work to do here. I'm going to subtract 6. I'm rearranging it. Divide everything by 2. Then I'm going to factor. So that's positive 3 and negative 1. And then when I solve it, I get 2 y coordinates. So at 0, negative 3, and at 0, positive 1. So where do we have the slope equal to 0? At 0, negative 3, and at 0, 1. Then I have to do the second derivative test, right? So let's do the second derivative from this. I have to do the quotient rule. So the quotient rule is the bottom times the derivative of the top, which is just negative 2. Subtract the top times the derivative of the bottom, which would be 4, but it's 4y prime. Needs a hook. And then 4 plus 4y, and we square it. That's the second derivative test. So we know what y prime is. So I'm going to simplify this just a little bit. Negative 2 times 4 is negative 8, and negative 8y. Positive 4x. And that negative, well, we have 4. I need, where there's a y prime, I'm going to put in negative 2x, 4 plus that. So y prime is that. So where there's a y prime, I just plug in what y prime equals. Simplify it. Oh, we want to do it at 0, negative 3, and at 0, 1. So let's do 0, 1 to begin with. So notice 4x times something. So if you plug in 0 for x, that whole thing is going to eliminate. And then plug in 1 for y, and you get negative 16. And if you plug in 1 here, you get 8 squared, 64. But you get a negative answer. So a negative answer means it's concave down. So at 0, 1 is a relative maximum, because when you plug it in, you get a negative answer. We're going to do the same thing for 0, negative 3. So for 0, negative 3, again, when you plug in zeros, that's why I didn't do much more here. If you plug in 0, you get 0. So plug in negative 3. And if you plug in negative 3, the bottom's always going to be positive. And that's all I care about. Because when you square it, whatever the number is, it's going to be positive. The top, though, it's going to be positive 24. Take away 8. Oops. That's going to give you a positive 16. So when you plug in 0, negative 3, you get a positive answer for the second derivative. That means it's concave up. So that means this one is a minimum. So a positive answer for the concavity means it's concave up, which means that point created a relative minimum. Now the second part to it, so the first part has to do with horizontal tangents and using the second derivative test. We did that. I'm going to squeeze 19 in right here because 19 says vertical tangent lines. So for that, just want you to see what I'm doing. So 4 plus 4y. So I took the first derivative, and vertical means undefined. So if it's a vertical tangent, a vertical line has a slope that's undefined. So when it says vertical, the slope is undefined. So back here to the first derivative, I take the bottom equal to 0. So if the denominator is 0, it's undefined, it's vertical. It's a vertical tangent. So take the denominator equal to 0. You get y equals -1. And then to find the x coordinate that goes with it, you plug that into here to solve for x. So if you plug -1 in, you get -2, add 2, so it's just plus or minus the square root of 8 is what you get. So there are 2 points. Just check with my answer key, make sure I'm telling you the truth. So positive and negative root 8. Yep. So for number 19, where are the vertical tangents? So it's at positive and negative root 8 and 1. So 2 of them, one at positive root 8 and 1 and one at negative root 8 and 1. All right, we're almost there. Number 20. At least we're doing it together. All right, this one actually won't be too bad. From 20 to 23, we'll do them all together. 20 to 23. So match the graph in the top row with the appropriate graph of the derivative underneath it. So for number 20, that's a parabola. And so that would be like x squared. If I took the derivative of x squared, you get positive x. So 20 is going to match with a slanted line. So 20 goes with B. 21, what is that the graph of? X cubed. And if you take the derivative, you get 3x squared. So x cubed matches with the parabola. Now I see 2 parabolas down there. So which one would be the one that matches better? And so because of the 0, 0 part for 21, see how we have a point of inflection at 0, 0? It's like right there at x cubed. It's going to match with C. 22 is a slanted line. And what's the slope of a slanted line? That's a constant number. It's a positive constant number. So 22 matches with A. All right, last one. 23. 23 obviously is going to match up with the one you haven't done yet. But I want you to see again, 23 is an odd function. It goes up to the right and down to the left. And when I think of the derivative there, let me just show you in terms of like seeing it. We're going to do more work on understanding the graph of the derivative on the next lesson. But let's just get like a head start in understanding it. So I mean, this is what I have so far. So the first one is x squared. The derivative is actually 2x, but it's a slanted line, so it matches with B. X cubed, that's 3x squared. They match, right? So find the graph that's 3x squared. 22 is a line, so the slope of a line is a positive constant number, so it's horizontal, A. This one, How does this one match? So what we're looking for is increasing and decreasing. So the derivative tells you where that is. So first it increases, so it's above, and then it decreases, so it's below, and then it changes to increasing. So I want you to notice that and match it up here. So up to like -1, it increases. So up to -1, it's above. Then from -1 to +1, it decreases. From -1 to +1, it's below. And then after +1, it increases. Above, below, above, and that's why it matches. We're going to do more work on that on the next lesson. And at first, and at second, and at third, it might be confusing until we get it. 24. So, this is it. Darn it, right? 24. Man, felt like we've taken a year away here. But, man, we do it together. We fight through this together. We learn through this together. That's what I like. Find or estimate the slope of each graph at each letter point. So from A to B, I can just count, rise over run. So for 24, if you go down, how many, and to the right, how many? So down 2, to the right 3, I get -2/3. Oh, at each letter point. So at A, it's -2/3. You know what? B is also -2/3. The slope didn't change from A to B. It's the same slope. So both give you the answer -2/3. C, what's the slope at C? And the answer is 0 because it's a horizontal line. What's the slope at D? It's a vertical line, so that slope is undefined. And I'll show you my work when I'm done. E, so that point is in the middle of decreasing. So if you drew a little line that touches it there, I think you could see the slope is -1. At F, if you did the slope, it would be 0 because it would create a horizontal line if you just touched the point at F. So a turning point has a slope of 0. G, see how it's increasing? If you drew a line there, you could say that at G the slope was +1 approximately. H, see how it's increasing? So if you drew a line there, it's steep, maybe 2 or 3. I, what's the approximate slope? Is it positive or negative at I? So I'd say about -1. And then at J is a turning point. So anytime you have a turning point and you draw a line there at that turning point, it's right there at a turning point, the slope would be about 0. It would be 0 if that's the turning point. So let me show you my work. So if you see a point, could you tell me the slope? Negative, positive, 0, undefined. Calculus is about slope. Derivative is about slope. That's why conceptually it's important to be able to approximate a slope off a graph. So this is what it looks like. A and B are -2/3. C is 0, undefined. And then the other points, E, -1, F, G, H, I, J, looking off the graph. I am so proud of you that you got to the end of this assignment. This is one of the toughest assignments that we've had so far, but we got through it together and try to learn from it and fight through it and then fight until we get it. Any question, go back and look at it again, or ask me a question when we see each other and go through it that way. I am Mr. G Math, over and out, until next time.